Alright, this video we're going to combine exponential and logarithmic function talk by talking about how to solve equations involving exponentials and logarithms. Let's just have a handful of examples here. It turns out that logarithms are how you solve exponential equations. So it's kind of a neat little introduction to future topics, but the prereqs here will be solving equations. You have to know how to solve all types of equations, not including at this point exponential and logarithmic equations, because we'll learn that here. And you need to know everything about exponential functions, and you should know what a logarithm is and how to simplify a logarithm or evaluate a logarithm. So we're going to solve the equation 10 raised to the negative 5x power is equal to 37. Now, prior to solving this, I want to remind you of the definition of a logarithm. Logarithm is just the base b logarithm of x is just the exponent to which b must be raised to yield x. Now, again, as I mentioned when I first introduced this definition, I never memorize anything around that language. I just worry about the notation. If somebody gives me log base b of x is equal to y, I know using the circular argument that b raised to the y power should equal x. So these two things, this in blue and this in black, mean the same thing. Okay? Now the question is, how is that going to help us here? Well, every time that we've had a problem, an equation in mathematics up to this point, we've had a way of undoing operations, like, undoing the multiplication on that x there of negative 5, or undoing a subtraction of 15, or whatever it may be. In this case, I want to undo this base 10 here. So the way you can do it, and this is the way that I teach it, not the way that books teach it, I take the logarithm base 10 of both sides. Now, before I get too far into this, I want to illustrate something for you. So I'm going to first start by saying, well, let's take the log base 10 of both sides. So let's write this side as 10 raised to negative 5x, and the right-hand side is 37. So I'm taking the log base 10 of both sides. Now, like I said, before I will go any further, I want to show you something. Recall that if you want to solve like the square root of x minus 1 is equal to 3, you want to undo the square root. And the way you undo the square root is you apply a function to both sides. And the function that you're applying to both sides is the squaring function. So you square both sides and you get x minus 1 is equal to 9. That squaring function that we apply to both sides undoes or unlocks the x minus 1. It undoes the square root and it unlocks the x minus 1. Same thing for, let's say, 3x is equal to 17. I need to do something to both sides that will unlock this x. And the thing that I'll do to both sides is divide both sides. That's the function I'm applying there. So that gives me that x is equal to 17 thirds. Thirds. Just like those two examples, when I look at this problem right here, I'm thinking I need to do something to both sides to unlock that x. And a logarithm, really truly the only reason why the logarithm came around is so that it could unlock exponents. Recall that we have a theorem that states log base b of b to the p power is just p. I don't like to memorize that. I just remember, use a circular argument. When somebody hands you log base 7 of 7 to the third power, you should ask yourself, that's going to equal something. It equals some power. 7 to what power is equal to 7 to the third? Well, 7 to the third power is equal to 7 to the third. So that's why I don't want you to memorize this. I want you to know the logic behind it. Now, going back to our problem, whoops, wrong page, there we are. Going back to this problem, log base 10 of 10 to the negative 5x, well, that's just going to turn into a negative 5x. equals log base 10 of 37. And now all I need to do to isolate the x here is to divide both sides, basically to undo this multiplication by -5, which calls for a division of -5 on both sides. When you divide both sides by a -5, on the left-hand side, -5 over -5 is just 1. So I get a single x is equal to a negative log of 37 all over 5. And notice that I didn't put that 5 inside the logarithm because it's not inside the logarithm. It's outside the logarithm. You have to keep it out. So let me figure out what this answer is. I need a calculator for this because the fact is logarithms in general you're going to have a calculator for. So I'll just say what's the negative log of 37 and that logarithm divided by 5. Turns out, rounded to the nearest thousandth, that this is going to be a negative 0.314. Now let's try another example because I think that this is well worth several examples. So let's go ahead and solve this. Now I look through this equation. Now I'm just going to go back into the mode that I've taught this entire time through all these lectures. When I see only one version of a variable in a problem, I immediately start asking myself, what happened to that variable? So I zoom into that variable and I see the first thing that happened to it is somebody multiplied it by 3. The second thing that happened to it is they raised it. They put it in an exponent. So they said 10 raised to it. I have no other way to write this other than to say 10 raised to the thing. Okay, whatever I could do. It's up here. This is where the x is up here. I have no other way of saying that. After it's been raised into the power part, the exponent of the 10, next thing that happens, now just zoom in, we're talking about we now have 10 raised to the 3x. That gets multiplied by 2. Next thing that happens is all that stuff gets to lose 3.5. Now to untie all of this to find out the value of x, see this is what tied x up into a knot. So to untie a knot, we undo each of these steps, starting with the last one that was done. So the last thing that was done, they subtracted 3.5, so I'll add 3.5. The next to last thing they did was they multiplied by 2. I'm going to divide by 2. The next thing they did was raised both sides base 10, or they raised that base 10, sorry, not both sides. And I know how to undo raising something base 10. It's to take the log base 10. And then finally, they multiply by 3. I'm going to divide by 3. That's my tactic right there. That's my list of tactics. So first thing I'm going to do is add 3.5 to both sides. When I do that, I get 2 times the quantity 10 raised to the 3x is equal to, let's see, that's 14.3. So that's done. The next thing I'm going to do is divide both sides by 2. So when I divide both sides by 2, I'll do this in gray here. These 2's will cancel nicely, and we get that we have 10 to the 3x is equal to, well, you could either leave it as a fraction. I probably would. I'd probably just leave it as a fraction like that for now. Although that's not a proper fraction, by the way. Fractions usually do not contain decimals. But I know I'm going to grab a calculator in a moment, so I don't mind having that like that. My next step would be to take the log base 10 of both sides. Log base 10 of the left-hand side and log base 10 of the right-hand side. And again, the reason why I do this is because logarithms unlock exponents. So log base 10 of 10 raised to the 3x will just become 3x. On the right-hand side, we still have log of 14.3 all over 2. Finally, I divide both sides by 3. So I get the following. X is equal to that logarithm, log of 14.3 over 2, all being divided by 3. And I can reach for a graphing calculator that I've had waiting this entire time. Type in log 14.3 divided by 2, and the logarithm, and divide that by 3. 0.285, roughly. So that's how it's done. A lot of students, if they catch my lectures, if you haven't seen a lot of my lectures prior to this, you're going to find that this method, what I'm saying is, this method of what happened to X might be very foreign to you, but it really does carry you through all of mathematics. And it's such a simple idea that you have somebody that just has this value of X, this unknown value here, and they do something. They're tying it up so that they're hiding the value from you. So you just use the order of operations based around X to figure out what they did. You start at X and go, what's the first thing they did? Well, they multiplied it by 3. Then they raised it base 10. And then they multiplied that by 2. Then they subtracted 3.5. That's all the knot that they tied around X. And to untie that, you undo each of those things, starting with the last thing they did, because it's how you untie a knot. So let's attempt this again. And again, I'm going to write out all the list of steps here, because I see only one version of my variable in this entire problem. So I know that I could solve for this variable just by listing out what happened to that variable. So let's see, I zoom into X here. The first thing that happened to it actually is it got multiplied by a negative 5. The second thing that happened to X after it becomes a negative 5X is somebody raised it base 10. So they took it and raised it base 10. That's my only notation that I know how to write with it. But once they had 10 raised to a negative 5x, they multiplied that business by a negative 1, right? To make it a negative 10 to the negative 5x. Be very careful when you're doing this. The next step, the next thing they did to really try to throw you off the chase, is they added 1. Because that's a positive 1, really, that they're adding to this. So now I'm done inside the parentheses. The last thing they do is they multiply by 110. So I have a list of things here that I really need to undo. The first thing that I'm going to undo is the last thing that they did. They multiply by 110. I'm going to divide by 110. And then right before they did that, they added 1. I'm going to subtract 1. Right before that, they multiplied by a negative 1. I'm going to divide by a negative 1, but let me just let you know, dividing by a negative 1 is the same thing as multiplying by a negative 1, so it doesn't really matter to me how you do that. Prior to that, they raised that business to base 10. Well, I know how to unlock an exponent or how to undo raising base 10. It's a log base 10. That's my dog, if you can hear my dog. Finally, to the first thing they did. They multiplied by negative 5. I'm going to divide by negative 5. Now let's see what happens with each of these steps. So I'm going to do this in blue this time. If I take this business right here and I divide both sides by 110, I will end up with 1 minus 10 raised to the negative 5x is equal to 288 divided by 110. Notice that I didn't simplify that fraction because I know I'm going to be grabbing a calculator. I just know it's going to happen in this problem. So I'm not going to bother with simplifying fractions. So this step is done. I will now subtract 1 from both sides. So I'll get this 288 over 110 minus 1. And again, I'm not going to combine those numbers because I'm going to grab a calculator in a moment. I'm going to divide both sides by a negative 1, which means swap signs on everything. Well, okay, maybe not that exponent, but everything else you could swap signs with. So it's a negative 288 over 110 plus 1. Take the log base 10 of both sides. This will take 2 lines here because I'm being kind of slow with it, but eventually you can kind of be fast here. Log base 10 of both sides. It always happens as long as your base on your exponent is 10, the log base 10 will always cancel it out. A lot of students, once they get used to the idea, will tend to they'll not even write the log base 10 of 10 to the negative 5x. A lot of students, myself included, when you take the log base 10 of both sides, you know that left-hand side is just going to be negative 5x. So it's just something that you kind of get used to. Now, finally, divide both sides by a negative 5, and you'll get the final answer. X is equal to a negative log base 10, but I'm just going to write it as nothing because that's what we assume when you're base 10, of a negative 288 over 110 plus 1, all divided by 5. I just threw the negative out front. So now if I want to approximate that, get a decimal approximation, I'll put a negative log of negative 288 over 110, and that's being added to by 1. Close out that logarithm and then divide the whole thing by 5. Uh-oh, we've got a problem. It's a non-real answer. The first thing you should do when you get a non-real answer like this, check that you did everything correctly. We actually did, but I'll just walk through this. Let's see. What happened to x? It got multiplied by a negative 5. Got that. It was raised base 10. Got that. Multiplied by a negative 1. Got that. Added to by 1. Got that. And then that whole thing was multiplied by 110. Got that. So divide by 110. Subtract 1. Divide by negative 1. Do the log to undo the exponent. And divide by negative 5. Let's see if I did all that. Divide both sides by 110. Boom. Subtract 1. Yep. Switch signs on everything. Take the log base 10 of both sides. Yep. Divide by negative 5. Sure. So what is wrong? Let me hit quit and let me just check to make sure that this is all done correctly. Negative log of negative 288 over 110 plus 1, all being divided by, everything looks correct. So what could possibly be the issue? Well, turns out there's no answer, no real answer. The reason why, other than the fact that the calculator told us, is that on the inside of that logarithm, a negative 288 over 110 plus 1, that ends up being a negative number. So let's investigate that. What if I told you I had a log base 10 of a negative number, and I told you that's equal to, let's say that's just equal to some number 5 or whatever. We can make up any number we want, but maybe I'll say it's just equal to x. So the question is, 10 to what power will equal a negative number? 10 to what power will ever equal a negative number? Well, there's no power of 10 that will ever turn out a negative number. 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, they're all positives. Huge positives. 10 to the negative first, 10 to the negative second, 10 to the negative third, those are just fractions, but they're all still positive. There's no way to make a power of 10 turn into a negative. And in fact, there's no way to make a power of any positive number turn into a negative. So because this in here was negative number, there was just no way we could get an answer. So there is no solution to this. No solution at all. Got to watch out for that. But that's also a great point to make. So when we defined a logarithm way back when, I didn't really, that's definition of common log. There we are. When we define the logarithm, the one thing I didn't really mention here, because it's more of a theoretical point, is that the inside, the interior or the input for a logarithm, the x value must be positive. X has to be greater than 0. And that's a very important point to make at this point. I kind of take my time getting there because I want to make sure that we cover all the basics of logarithms. But the fact is, now we can start worrying about that in the future, that we have to make sure that the inside, the input for our logarithm, is positive. Because if it's not, remember, b is always positive, y is just a power, so you have a positive number to some power, that's always going to be positive. So x has to always be positive. These two that link up always have to be positive. Now, I want to mention something that some instructors will get on my case about when instructors or maybe other textbooks or whatever they introduce this idea. They really go from the definition of a logarithm. They say, well, okay, listen, the base of this exponent is 10. And remember how a logarithm is set up. 10 to what power equals? So 10 to the negative 5x power is equal to the inside. That's how they'll often do it. But I really like the idea. I don't like to use that method because I like the idea of applying the logarithm to both sides like you always have. Add 2 to both sides, divide both sides by 3, square both sides, take the square root of both sides. So why should I all of a sudden change my tactic once I get here? I'm going to take the logarithm of both sides. It still works out to be the same. Okay? So if you happen to read in your textbook that they use this method where they say, now switch to logarithmic form using the logarithm, definition of a logarithm, you could just ignore that and just say, no, I'm going to take the log of both sides and use that theorem that says log base 10 of 10 raised to a power is just going to be the power. Okay. For the last three examples in this example set, this solving set, I'm going to switch gears. We're going to solve logarithmic equations. So those were all exponential equations, and we use logarithms to help us solve them. But sometimes you're given logarithmic equations, especially with applications. You're often given logarithmic equations. And so I need a way to solve this. Well, the only way I know how to solve this is to really switch it into exponential form. So b to the third power is equal to 8. So that's how I'm going to rewrite this. B to the third power is equal to 8. Well, now I will undo the third power by taking the third root of both sides. Right? Third root undoes third powers. And by the way, applying that function to both sides, the cubed root function to both sides. So just like we, in the last few examples, were applying the logarithm to both sides. So still keeping the same idea. Cubed root of a cube just turns into b. And the cube root of 8 is 2. So the answer here is b is equal to 2. You should always check your answer, especially with logarithms. Logarithms, you have to be kind of careful because some answers are not good. So just take a look. 2 raised to the third power, is that 8? Yeah, it is. So let's try this one. Log base 2 of 3x minus 1 is equal to 5. Again, when somebody hands me an equation in logarithmic form, I generally like to switch it to exponential form. This will tell me that 2 raised to the 5th power should equal that junk on the inside. So 2 raised to the 5th power should equal 3x minus 1. And all of a sudden I realize, oh, I could solve this. 2 to the 5th power, that's just 32. Add 1 to both sides. Divide both sides by 3, and you get that x is equal to 11. Again, check for realism. One thing I know is that the interior or the argument or the input of a logarithm must be positive. So always check to make sure. So check for positivity. Okay, so let's see, plug in 11, you get 33, minus 1 is 32. Okay, that's good enough for me. It's positive, I'm okay. Now this example, we have a little math to do beforehand. I'm going to subtract 5 from both sides, and then I'm going to go ahead and divide both sides by 3. So 3 log base 7 of x, subtracting 5 from both sides gives me 2, dividing both sides by 3 gives me log base 7 of x is 2/3. And finally, I'll switch this now, because you can't switch, I'll switch it now to exponential form. And the reason why I waited till this point is because you can't switch to exponential form until you have just a single log base something of something on one side. So you have to isolate that first, and then you could switch to logarithmic form. Remember, this means that 7 to that power is equal to x. It's actually kind of nice because it gives us the answer immediately. 7 to the 2/3 power is what x is equal to. You might want to approximate that using a calculator. If so, just bring up a handy dandy graphing calculator, type in 7 raised to the parentheses 2/3 power. 3.659. So roughly 3.659. Now, honestly, I find that exponential and logarithmic equations, problems that involve solving using exponential and logarithmic equations, are the most entertaining because they usually are the ones that involve the most realistic information. So here, the population of the state of California increased during the years 1960 to 1970 according to the following formula. 15 P of t, population at time t, is equal to 15,717,000 times 10 to the 0.0104 t power, where t is the number of years since 1960. Now let's just recall, because we're going to have to, the standard form of an exponential function is p of t is equal to p naught b to the t. In this case, the base growth rate or growth factor is 10 raised to the 0.0104. Okay, so let me just put this in its proper form. P naught, our initial population, is 15,717,000. And our base is 10 raised to the 0.0104. This is kind of an interesting little note. And this is, again, is the initial population, and this is the growth factor. So they ask, what's the population in 1970? So I want to evaluate this function, not at 1970, but at 10. And the reason why is, well, that's 10 years since 1960, and t is the number of years since 1960. So if I plug that in, and I'll just go ahead and I'll go ahead and write it out. 15,717 with a few zeros after it times 10 to the 0.0104 times 10 power. Well, you can grab your calculator and go ahead and figure that out real quickly. 15,717,000 times 10 raised to the parenthesis 0.0104 times 10. I know that we all know what that is, but that's okay. All right, so hit enter, and we find the population. Let's round to the nearest person here. 19,969,613. So roughly 19,969,613. That many people. Almost 20 million people. So in 10 years, the population grew quite a bit, actually. Assuming the same rate of growth, so assuming that this growth factor here stays the same, estimate the population in California in the years 1980, 1990, and 2000. Well, that's just a lot of the same question, so I'm just going to concentrate on just finding the population in the year 2000. In fact, this is from the second edition of the Yoshiwara Modeling Functions and Graph textbook. So let's actually do 2020. Let's see, according to this, let's see what the population in California would be in 2020. So how many years after 1960 is that? Let's see, well, that's 60 years after 1960. So I'm going to just plug that into, again, this function. All this you should be able to do. This is old hat. This should be old hat to everybody. But it's still kind of fun and interesting. So let's go ahead and do this. 15,717,000 times 10 raised to the start of the parenthesis 0.0104 times 60 and end your parenthesis. And here we go. 66,125,000 and what is it, 604. I'm very curious. I'm going to tell you right now that this is likely not true at all. Actually, it really is not true, because I know that the population of the United States right now is probably around 380 million. So I couldn't imagine that California has this many people. And as you can see right here, current population, well, as July 2009 from the U.S. Census Bureau, is about 37 million people. So why is this function wrong? I always enjoy asking these questions in classes because I think that it's great to illustrate kind of the fallacies that you have in a daily life. This is wrong because, well, when you use a model like this, it's called an exponential model. Say it's accurate for only a few years, between the years 1960 and 1970, probably. Maybe a few years after 1970, and that's about it. That's as good as models are, but they don't go out that far. The further that you go out in time, the less accurate they are. And in this case, we see it's so inaccurate. We've actually overestimated almost by 100%. We've almost doubled it. So, just a word to the wise. When somebody quotes you, well, the population is estimated to be, 25 billion on this planet in 2025 or something like that, you have to take it with a grain of salt, because the fact is they're predicting using formulas that are only accurate out to maybe 5 years or something like that. So just be very, very skeptical of things, claims about far in the future. Okay, on we go to part C here. When did the population reach 20,000 people, or 20 million, 20 million people? Let me erase all my work here so that I have some room to kind of work. I want to know when the population reached 20 million. Well, that means let the population be 20 million. And let's find out what t is. And this is why we need logarithms, because everything up to this point in this problem I haven't needed a logarithm for. But now I notice the only unknown in this problem is sitting up here in my exponent. And the only way I can unlock unknowns from exponents is to take logarithms of both sides. So, but first we're going to isolate this. We're going to get just 10 to the power by itself on one side. So I'm going to divide both sides by that 15,717,000. So I'll get this 20 million over 15,717,000. By the way, those zeros will cancel, so I don't have to write such a large number. That's supposed to equal 10 raised to the 0.0104 t power. I'll take the log base 10 of both sides. So taking the log base 10 of the left-hand side gives me 2,000,15,717. I went ahead and just canceled out these zeros. I'm allowed to do that. I basically divided numerator and denominator by 1,000. On the right-hand side, when you take the log base 10, it just returns the exponent, because I'm taking the log of the same base of that base 10. So log base 10 of 10, those two kind of cancel each other out. It's not really true, but it brings the power down. So this becomes 0.0104 t. Now remember, I'm trying to find out what t is. T is just the number of years since 1960 that it took for the population to become 20 million. So I'll divide both sides by that value of 0.0104. Get this log of 20,000 over 15,717 being divided by 0.0104. And now I just grab a handy dandy graphing calculator and I punch it in, right? Log of 20,123 divided by 15,717 close out the logarithm and divide that by 0.0104. So, how many years did it take us to reach 20 million? 10 years. It's roughly 10. 10 years since 1960. So in 1970, the population reached 20 million. Now the process is basically the same for part D, so I'm giving you the answer and I want you to go ahead and try to do it yourself. Okay, so that's because really it's just going to be me repeating the same steps. The last little bit, graph your function with a suitable domain and range and verify your answers. That's if you have a graphing calculator. And it's great to do anyway, just to check your answers. So clear out any old functions you have. You could just enter in here 15717. Whoops. 15717. Jeez. 000. Times 10 raised to the parentheses 0.0104 x power. Okay. Now choose an appropriate window. Let's see. The minimum value for time, we're going to put as 0. The maximum value for time, let's go ahead and go up to 1990. So that's 30 years later. Okay. The population, don't start at y equals -10. Don't even start at y equals 0. The minimum population is 15,717,000. So I'm going to start my y values at 15,500,000. And then I'm going to end my population probably around maybe 35 million. Okay? And then we go ahead and hit graph. I'm just going to do that, just so I have a nice window here. Now, it says verify your answers. Here's how you verify your answer. It's a very cool tactic. You could either hit trace and say, okay, well, let's see, what's the x value, the input, in the year 1970? Well, that's 10 years after, so let me type in 10, hit enter, and you see, oh, it's roughly 19,969,000. Well, that's almost 20,000. I'm good with that. That's one way you could do it. Or, kind of a cool way, is to graph the horizontal line 20 million. If you graph that horizontal line, that tells me the height or the population level reaches 20 million right here. And you could use the calculator's intersect feature to find what time that occurs, what the intersection point is. The way you do that is through the calculate menu, all accessed again in these above 5 buttons, but the calculate menu is right through the trace button. So second, trace, and notice the 5th option says intersect. It asks me, where's your first curve? I'm just going to say that's perfect because that's the first curve. It says, is this your second curve? Yep, it sure is. Then it says, hey, take a guess as to where they cross. Well, you don't have to get too close. That's good enough. And then let it go. It intersects at x equals 10, which is 10 years after 1960, which would be 1970. And you could do the same thing with 30,000. So here's the exponential function. There's 30,000. Let's find where they intersect. Second trace. Choose option 5. Yep, that's the first curve. Yes, that's the second curve. Then get kind of close, but you don't really have to in this case. But I'm just going to get a little bit close here. Hit enter. And there you go. It happens 26.99, so I just rounded up to 27. 27 years after 1960, which would be 1987. That's how it's done.